Good morning, or good afternoon if it's seventh hour. We're going to go into light and lenses today. We talked a little bit about the light and kind of just the properties of white light a little bit yesterday and Thursday. So now we're going to move on and kind of talk about how light behaves rather than the different classifications and the different types of light. So the first one we're going to look at really quick, a review about the parts of the light wave. So what I want you to do, kind of off to the side, somewhere on your notes page, either on the front or the back, just kind of take a second and write down the answers to A, B, C, and D. I'm going to give you about 15 seconds or so. If you need more than that, then just hit pause, okay? And then I'll let you check and see. Alrighty, so if you need more time, again, just hit pause. No big deal. But I'm going to go over these and we'll see what you know. A right here, remember, is just the height of letter B, or the height of letter D. So there's the distance there. That's called amplitude. Letter B is going to be the topmost part of the wave, which is a peak. Letter D, I'm going to skip ahead, this is the trough, the lowest part. And then letter C is the distance between two troughs or two peaks, and that's called the wavelength. So hopefully you got all those correct. In your first box there, off to the left side, there's a couple of definitions. So the first one we're going to look at is pigments. Pigments are molecules that can absorb certain wavelengths or different colors. So, for example, if you're wearing an orange shirt, you have this pigment that is designed to absorb every color but orange, every wavelength but the orange wavelength. Instead, it's going to reflect that orange wavelength, so that's the color that you see. Okay? So, depending on the particular pigment, that's going to determine what wavelength colors that particular pigment will either absorb or reflect. So, the one that I have for an example here is chlorophyll in plants. And what chlorophyll in plants does is it's going to absorb the red and the blue wavelengths, and it's going to reflect the green wavelengths, which is why our plants look green. Because that chlorophyll is that pigment, so it's going to absorb every other color but green, and it's going to reflect that color green. So black is absorbing all colors. That's every single color. You know, red, orange, yellow, green, blue, purple. Okay? White light is when something reflects every light, every wavelength color. Alrighty, your next term down is matte, and this is going to describe the texture of the surface of your object. I know this is a long time ago, and you guys probably don't even remember this, but your parents probably would. A long time ago, we actually had cameras with film canisters in them. I don't know if you guys ever used those, but we had to take those out and get those pictures developed. And they would always ask you, because we didn't have them in digital form, so we couldn't just print them. They were on actual film. And so we'd have to send it off and order everything. And one of the options was always, do you want your pictures to look glossy or do you want them to look matte? More often than not, your professional photos that you get done, so like your school pictures, any team sports pictures, if you look at it, it doesn't look shiny and glossy. It's kind of, if you really look at it, it looks kind of rough. Now, it doesn't feel necessarily rough, but you can kind of see that it's kind of rough. It's not super smooth and glossy. Usually the pictures that you print at home, those would be glossy pictures. So way back when, we would pick, do you want matte or do you want glossy? And so matte is going to affect how the light is going to reflect off of that particular object. Okay, so what I would write down if I were you is that it describes the texture of the surface of the object and means that it contains pits or scratches. If you want to write down that it means it's not shiny and smooth, that's fine, but you don't have to. So the next ones we're going to look at, light can pass through objects in 3 different ways. It can be an object can be transparent, translucent, or opaque. And those are your next 3 words on your notes right there. So, transparent, translucent, opaque. Yep. Okay. Sorry. Okay. Transparent. If a material is transparent, that means that most of the light can pass through it. Means that you can see through it. Sometimes you'll hear the government say, "Oh, we want a transparent government," meaning we don't want to hide anything. We want the public to be able to see everything we're doing. You know, if somebody's trying to promote a transparent process, like we want this process to be transparent, that means they want you to be able to see every part. So it's kind of what it means here with the light. It just means that almost all the light can pass through. Now there's some light that does get absorbed by your material, but most of it goes all the way through. Your example would be your windows in your house. For the most part, those are going to be almost completely transparent. Now, your car windows might have a like a sun layer, that kind of like a sunglass layer. Usually it's more apparent in the back seats and not in the passenger and driver seats, just because of safety issues. But that doesn't let as much sun through, but it's still mostly transparent. So the example I have here is this beaker, this glass beaker, because it's going to let almost all of the light pass through it. You're going to be able to see all the way through it. If something is translucent, if you held up a light behind it, you might not be able to see the object clearly, but you might be able to see the shadow of the object. So with translucent materials, they're going to allow some light to go through it, but they're going to absorb some light too. It's kind of 50-50. So sometimes you can see features, but usually you can't see specific features. This example right here is a plastic pouring cup. So it's a thicker plastic, I don't know, because you can't really see through to the wall behind it. However, if you put a light behind it and you put stuff in there, you'd be able to tell that there was stuff in there. You just might not be able to tell what color it is. You might not be able to see if somebody put a ball in there, you might be able to see that there's an object in there, but you might not be able to see any physical features of that ball. So you can kind of see the object through, but not perfect. It's kind of like if you held a sheet up and you shine a light behind it and had somebody walk in front of it, you could tell there was somebody there because there's some light getting through, but you can't see all of it. You could just kind of see their shadow there. Or their silhouette, rather. The third way that light can pass through, which really isn't passing through at all, is opaque, which means that no light gets through, and all of the light is absorbed by that particular object. So the mug here, the 2 mugs here, the metal mug and the ceramic mug, if you put a light behind it, you wouldn't be able to see anything. You wouldn't be able to tell, like, just looking there, we have no idea if there's liquid in there. We have no idea if there's a ball in there. We can't tell because light isn't shining through it, isn't passing through it. If there was a ball in here, we'd be able to see that there was something in there. We just may not be able to see exactly what it is, but you could at least see that something was in there. Same with the transparent object. You would actually be able to see everything then. So just make sure you know these 3 vocab words: the transparent, translucent, and opaque. Alrighty, your next set is going to be reflecting and refraction. My guess is you've heard of the word reflect. You may not have heard of the word refract. So this last slide talked about how light can pass through objects. Now we're going to talk about how, specifically how light can pass through objects or how it can interact with objects. Okay, technically there's 3 ways, but we're going to talk about, I only want you to define 2 of them. If light is reflected, that means it's bouncing off of the surface. So we kind of talked about reflection and absorption a while ago with the pigments. So a reflection here, the light is coming in here and it's hitting the surface and it's not going to be absorbed, so it's going to bounce off. Okay, if it gets absorbed, it's going to just stay in the surface. It's not going to get reflected off. So when I say reflection, it means bouncing off a surface. Light is bouncing off of the surface. If I'm talking about light refracting, I'm talking about when the light is actually going to pass through the surface and then it's going to change direction. It's going to change direction because this out here, this air out here, as it has a different density than this surface right here. And whenever you change densities, how close together molecules are, light will get bent. The easiest way, the best example I can give you, so if you've ever noticed when you have a straw in a glass and you can see through the glass, the straw oftentimes looks like it bends, like it's split. That it starts going down one way and then it splits through another. Okay, I've got a picture of it here in a little while that kind of shows that, but that's what happens with refraction, is it's going to pass through something with a different density and it's going to bend. So absorption, when light gets held onto by the surface or by whatever it is it's going into, if it's pigment. Reflecting means it's bouncing off, and refracting means it's going through it and it's going to change direction. So you can kind of see this arrow is going through here. It's not continuing on that straight path. It's going to get bent a little. Okay, on your right side, you've got these little boxes over here with the law of reflection. So we're going to do a law of reflection over here. We're not going to go down to light and density just yet on the left side. So, okay, the law of reflection. What this states is the bottom. It actually states down here, really, sorry. This is what the law, this bottom one. The law of reflection states that the angles of incidence and reflection are equal. So you have a little bit of room there, right? The law of reflection states that the angles of incidence and the angle of reflection are equal. That's all the law of reflection states. Okay? So, basically what that means, because we haven't really talked about what the angle of incidence or reflection is. When light is reflected off of a surface, you have 2 angles. The first one, I don't know if I have that. I don't. So you might write it kind of off to the side somewhere, because I just have what happens if the surface is uneven, which we're not there yet. But actually what you might do is just draw it on that. I think that's what I meant for it, because I created these last year, so I'm trying to remember what I meant. I think it's on the diagram. So just label the diagram there on the right, because this diagram should match this diagram here. The diagram on your notes should kind of match this. The angle of incidence is the angle that the light ray that's moving towards the surface. So this left angle, now it's not always going to be the left angle, because if the light's coming in from the right like this, then technically this would be the angle of incidence. Okay? The angle of reflection then is the light ray that's moving away. So this actually, as the angle, as the light comes in here and then gets reflected away, you technically have a right angle here, 90 degrees. So what it's saying is, if you drew that line straight through there, the angle right here, this angle of incidence as it's coming in, is the same as the angle of reflection over here. So what I would do is just label that diagram that the angle of incidence is part of the angle coming in, which is the angle on the left. Even on your diagram, it's the angle on the left, but like I said, it's not always going to be that. And then the angle on the right is going to be the angle of reflection. So that law of reflection just states that those two angles are the same. All right. So what does this mean when you hit an uneven surface, like a picture that has a matte coating with all those little pockets and pits versus a glossy photo that's completely smooth? That's what we mean by an even surface. It's a smooth surface. An uneven surface is going to have pits. Concrete, for example, would be considered uneven because it's got all those different pits and stuff. So when so underneath, what happens when it hits a surface that's uneven? So I would write this part right here. Even when the light hits an uneven surface, the angles are still equal. The light is just reflected off in different angles. What I've left down below then, where it says normal surface versus uneven surface, that would be you drawing these two pictures. The normal surface would be the even surface. Probably should have put those down as even or uneven, not normal. So with the even surface, this particular one has 5 light rays coming in and 5 light rays being reflected in a very nice, orderly way. This one, on the uneven surface, you still have it reflecting to where the angle of incidence is the same as the angle of reflection. However, the angle of reflection, but because they're going to hit at different points, the way that they're going to, the direction in which they're going to hit is going to be different. So this outside one here is going to come here and hit it just right, and it's going to send that particular light ray this way. This one coming in is hitting the inside of this pit, so it's going to then hit straight up here. So depending on where it hits on this uneven surface, it's going to determine which direction those light rays are going to get reflected off. So yeah, that's just do your best to doodle that one. If this doesn't make sense, this angle of reflection and incidence, I'm staying after school today, so you can come in and ask me any questions. And I'll be here also in the morning about 7:30 tomorrow morning, so if you still have questions, just feel free to come in and ask. We're going to talk a little bit about those different densities again. So now you're going to go back over to your left side where it says light and density. When light goes through a denser material, that's where we're going to start, okay? So don't write anything just yet. But this is kind of what I was talking about with refraction when the light gets bent. So depending on the density of what the light's passing through, whether it's glass, water, air, everything's got a different density. Density, remember, is how close are those molecules? Are they really super close together? If they are, it's going to be a dense material. If they're really spread out, it's going to be a less dense material. So light's going to be refracted or bent when it goes through different materials that have different densities. And this is the thing that I was showing you or talking to you about. If you've ever noticed this, air has a different density than water. Water happens to be more dense than air. And so it looks like the straw, we all know that the straw is one piece. It didn't actually bend. But just because of the different densities, the light's going to be bent. So it's going to look like that straw got cut in half. And if you actually look really closely, The straw here even kind of bends slightly as you look through it through the glass, because you're looking at this right now. We're just looking at it above the glass. Well, here we have to look through this. We have to look at the straw through the glass. So the light's getting bent slightly, so you can kind of see how the straw kind of bends a little bit. But then once it goes underwater, it really bends because the difference in densities between the water and the glass is a lot. So the angle of refraction is the angle that light bends when it passes through, is the light that gets bent. So the angle of incidence doesn't change, but the angle of refraction does. Okay? So what I would write here, when light goes through a denser material, it's going to bend more. That's what I would write down on your notes. When light passes through a more dense material, it's going to be bent more. If it passes through a less dense material, it's going to be bent less. And that's, like I said, you can kind of see it through the glass, which would be less dense. It's slightly bent, but then it's real, that image gets really distorted due to the light getting bent much more in the water, because the water is way denser than the glass. So that's what again, I'll say that one more time. On your left side there with light and density, when light goes through a denser material, it's going to be bent more. When light goes through a less dense material, it's going to be bent less. Alrighty. Oh, here it is. Just kidding. I got ahead of myself. So when light passes through the object that is more dense, it's going to bend more. The other thing I want you to write is that it's going to bend towards the normal. So add that in there too. When light passes through the object that is more dense, it's going to bend more, but it's also going to bend more towards the normal. I'll explain that here in a second. On the other one, when the light passes through an object that is less dense, it's going to bend away from the normal or bend less. So this left picture right, because we're getting absorbed, we're not getting reflected off here, so it's not going to go this way. And in this case, the angle of incidence and the angle of reflection aren't going to be the same because we're passing the light through different densities. So the law only holds up when you're passing light through something with the same density. So the light beams here, this is the normal. This dotted line is the normal. That's what we call normal, quote unquote. So this is less dense up here, more dense here. It's going from less dense to a more dense. So it's going to bend more towards the normal. So it's going to have a smaller angle of reflection. Over here, we're going from a more dense area to a less dense, so we're going to an object that's less dense. Finds the normal. So instead of going closer to the normal, you're going to bend further away. So your angle of reflection there is going to be a little bit bigger instead of smaller. All right, flip your notes over. We're going to talk a little bit about lenses now. Some of you who have glasses or contacts, this might actually pertain to you, depending on what kind of conditions you have with your eyes. Okay, so what a lens is, lenses are, I would add several things here. Number one is the second part. I probably should have moved that. A lens is any smooth, curved, transparent substance. Any smooth, curved, transparent substance. It's got to be smooth because light has to be able to pass through it easily without getting bent too much. And it's got to be curved in some way. It's just the definition of it, because that's going to help the bending of the light. And then it's got to be transparent, obviously, because it's got to let light go through it. Okay, so your eyes have lenses. Your, things like cameras on your phones, and then obviously your contacts in your eyeglasses are also lenses. Another thing I might add, actually I should look. What lenses do? I guess that's the first. I think that's the first one on your notes. What they do. They're going to focus the image by refracting or bending the light beam so that they come together or converge at one place. So that would be your first line there in that box. So it focuses an image by refracting or bending the light so that it can come together at one spot. You can kind of see it, that picture down here. It's passing through, bending these light beams so that it comes together in one spot here. That's what a lens does. Where do you find them? You can find them basically, like I said, anywhere, as long as it's smooth, curved, and transparent. So you can find them in an eye, camera, eyeglass. So that's what I would put there. Basically, it's asking for examples on where do you find them. What a focal point is, your next one, that's the point where the light beams all come together. So right here, that's the focal point. So the place where all the light beams come together is called the focal point. Okay, so what happens to the light when it passes through a lens? It gets bent. The next part, how does curvature affect the focal point? And that's right here. Curvature will change where the focal point is located. So that's what I would write. How does curvature affect the focal point? It changes where the focal point is. Curvature just means how much is the lens curved. Sometimes that can be due to how thick it is. It's like this lens right here is super thick. This lens, not so thick. Sometimes people ask, why are the images upside down? Well, follow the light beams. So this light from the head here is coming through. It's going to get bent, and it's going to go down here. So that's why all the images get flipped upside down. So our eyes, when we see things, your eyes will actually flip them upside down, and then your brain has to reflip it back upwards so that, everybody's still walking on the floor instead of walking on the ceiling. Again, like this right here where his hand is, you put it here, and then it bends and comes up here. So that's why everything gets flipped. So this one is super thick. The focal point's right here. It's much closer. Less thick lens, the focal point backs up a little bit because the lenses here are in the same spot. The discus man here is in the same spot, but the focal points are in different locations. And I might add, are different sizes. They appear to be different sizes also. Thicker lens produces a smaller image. The thinner lens produces a larger image. So, all right. Last box, convex and concave lenses, for those of you that are nearsighted and farsighted. Basically, we can classify a lens's curvature as either, so how much it curves, as either being a concave or a convex lens. If it is a concave lens, it means that the curve is scooping out. Or is scooped out, sorry. Caved in, think cave in. A convex lens means that the curve is bulging out. So this top picture here is the picture of a convex lens because it's bulging out. And then a concave lens means that the curve is bulging inward, or it's scooped inward. So you can kind of see that with concave lenses, it's going to make the focal point a little bit closer. That was convex lenses. Concave lenses are going to spread the light out a little bit more to push that focal point back. So that's what those two mean. Now, how does that relate to nearsightedness and farsightedness? Normal eyes, you're like your 20/20 vision. The light's going to pass through your eye here. It's going to hit the back here, the back part of your eye. In theory, that's where your focal point should be. So ideally, that's what it should do. Now, if you're nearsighted, look at the yellow. I don't know how you can see this, but look at the yellow. Your focal point's here. You want your focal point to be back here. So that's why things appear to be kind of blurry, because it's all focusing right here instead of back here where it should be, at the back of the eye. So then you use concave lenses so that you're spreading out the light a little bit more to move that focal point back further. So you can kind of see it's spreading the light waves out just a little bit more, and then this right here, by the way, this right here is a lens. We have another lens right here. That's why they start bending again. So it's spreading the light out a little bit, but then when it hits the lens in your eye, it'll focus it back to where it should be, which is back here. If you're farsighted, that means that your focal point is normally way back here, so it's really far back. So you get a convex lens in which we narrow those light beams a little bit more, so that, again, when they pass through that lens in your eye, it concentrates them even more, so that way, instead of getting your focal point back here, it's now up here. So that's kind of how the different lenses are able to work with nearsighted and farsighted. So, oh, it looks like it stopped screen sharing. So, there you go. Sorry about that. What I'll do, because I just realized that it cut out, I will attach these notes to the Google Classroom, so that way you can kind of look at that while I'm talking. So but you should have already gotten this. So I'll just make sure this is more of a note to myself. Just kidding. Sorry. So anyway, sorry about that. This is the picture here. I didn't realize that it cut out. So anyway, like I said, if this stuff still isn't making sense, please, please, please come in after school. If you can't stay after school, come on in tomorrow morning. I'll be here, like I said, about 7:30. And I'll be more than happy to kind of go over this with you. So if you do have any questions, please just ask. Otherwise, have a great day.